In this section, we're going to talk about conservative vector fields, which is actually something that I very briefly mentioned when I introduced the idea of vector fields earlier. But we're going to take a closer look at conservative vector fields and then connect that idea to our line integrals and talk about some other ways that we can compute these line integrals. All right, but first I have to give you some definitions. So I'm going to define the idea of a simple and closed curve. So basically a simple curve doesn't cross itself. So the two pictures I have, I guess on the left side are considered simple because they don't cross themselves at all, whereas the third one, not simple. And then a closed curve kind of means what it sounds like. It's closed, it's connected. So the one on the left is not closed, the other two are closed. All right, so here is an example. I'm giving you a plane curve, so a vector valued function r equals 2 cosine t, 3 sine t. And the question is this a simple closed curve? I guess the other thing I should have mentioned as well that I didn't, it's in the words and not in my picture, but if it's a simple closed curve, if it's simple, it doesn't cross itself, but it also it traverses the path exactly once. So it's not going to loop around over and over and over again. All right. Okay, so is the following a simple closed curve? The first thing I'm going to do is just check, is it closed? If this is a closed curve, the endpoints at t equals 0 and t equals 6 pi should have the same values. Right? If it's closed, the starting and the ending point should be the same. And so if you plug 0 into this function, you get 2 cosine 0 is 2, 3 sine 0 is 0. So you have the vector or the location 2, 0. If you plug 6 pi in, you end up getting the exact same thing. And so that tells me this is a closed curve. The starting point and the ending point are the same. All right, but is it simple? Does it cross itself? Does it repeat itself? And so to answer that question, basically, if it's simple, then when I plug in any numbers from 0 to 6 pi, I should never have repeated values. So I shouldn't get the same output at more than one place. And so in this case, because I have trig functions, I can see, okay, these trig functions are periodic, they're going to repeat themselves, and in fact, if I actually plug 2 pi, or even 4 pi in, I'm going to get the exact same value, because cosine of 2 pi is the same thing as cosine of 0, or cosine of 6 pi. Sine of 2 pi is the same thing as sine of 0, or sine of 6 pi. So if I plug 2 pi in, I get 2, 0. And so this is not a simple curve because it actually repeats itself. In this case, it just goes over the same loop over and over again. But potentially if you get the same value, maybe it crosses itself. Regardless, I was able to find a value of t that gave me the same output as other values of t. And so therefore, it is not a simple curve. So it's not a simple closed curve. When it comes to two-dimensional regions, we might talk about simply connected regions, and that would be a connected region is basically kind of same idea. It has a boundary that is connected. And if it's simple, there aren't going to be any holes in that boundary. So simply connected regions are on the top of my screen. Regions that are not simply connected because they have holes in them are on the bottom of the screen. All right, so we are going to be using that vocabulary a little bit later. But what I really want to focus on in this section is what's called the fundamental theorem for line integrals. So this theorem says, if we have a piecewise smooth curve given by r equals x of t plus y of t, or I should say x of ti plus y of tj. It's a vector valued function. Okay, so if we have a curve and we have a vector field that is conservative, a vector field that is conservative, here it is on the bottom of the screen, is one that is equal to the gradient of another function. So piecewise smooth curve, conservative vector field. Then when you integrate along that path over that vector field, the answer you get will be your potential function evaluated at your upper bound minus your potential function evaluated at your lower bound. This reminds me a lot of that fundamental theorem of calculus from Calc 1, that concept that we've been using all along, where you find an antiderivative and plug in the bounds of integration. It's very analogous to that. Okay, so what about conservative vector fields? So a conservative vector field is one where, again, this vector field is equal to the gradient of another function. And a vector field Mn is conservative if and only if derivative of m with respect to y equals derivative of n with respect to x. And I can't remember if I've explained why this is the case, but the basic idea is if our vector field is conservative, its components are basically partial derivatives of our vector function, or I said that wrong, partial derivatives of our potential function. Okay, lots of vocabulary. So basically, if we have a conservative vector field, it is equal to the gradient of another function. And so what this test is doing is it's basically saying, okay, well, if I take the derivative of f sub x with respect to y, it should equal the derivative of f sub y with respect to x. That's just comes from our partial derivatives, the fact that the order you differentiate with those partial derivatives doesn't matter. All right. Oh, I guess I wrote it down on the screen, what I just wrote down in red. All right, so here's an example. Is the field conservative? If so, find its potential function. So is this conservative? To check and see if it's conservative, our m is our x component, and the n is our y component, and so then we're going to take the derivative of m with respect to y. I got x times 1 over y, n with respect to x, 2x over 2y. These two derivatives, I can simplify them to be the exact same thing. So yes, this is a conservative vector field. All right, so if I want to find the potential function, the idea here is the m is my partial derivative of f with respect to x, and my n is my partial derivative of f with respect to y. So to find my potential function, I'm going to take my m, and I'm going to integrate it with respect to x. And I'm going to take my n, and I'm going to integrate that with respect to y. And that'll give me the pieces of the function of that potential function. Let me actually just do an example. I have a little bit more here written on the screen, but I think it's going to be easier for me to explain when I actually do the example. Okay, here we go. So to find my potential function, I'm going to take the m, the x ln y, and I'm going to integrate that with respect to x. So the idea that we're using here is our partial derivative with respect to x is x ln y. So our original function is going to be the antiderivative of that, plus we could have other terms that are functions of y, simply because when you take the derivative with respect to x, any terms that don't have x's in them are just going to disappear. But we will see those terms when we integrate our n with respect to y. So we can integrate our n with respect to y, and then we may have additional terms that don't pop up in that answer that are functions of x, simply because when you take your partial derivative with respect to y, any terms that just have x's in them might just, or will disappear. All right, so we are going to integrate x ln y with respect to x. And I get x squared over 2 ln y. And then I'm just going to jot down we might have additional terms that have y's in them. I move to my second integral, and if I do have additional terms with y's in them, they will appear here. Okay, so my second integral, I'm going to integrate x squared over 2y with respect to y. And let's see, I get, because this is the same thing as x squared over 2 times 1 over y dy, I get x squared over 2 ln y. And then I could have additional terms that have x's in them. Finally, I'm going to compare my two answers, and if there are any terms with both x's and y's in them, you should see them in both of your antiderivatives. And so it's a good thing that I see the exact same term, x squared over 2 ln y, in both of these antiderivatives. That has to happen. If they don't match, then you've made a mistake. And my antiderivatives don't actually have any other terms. And so this is my potential function, x squared over 2 ln y. And that's it. If there were extra terms, they would pop up when you're doing the antiderivative. So for example, just kind of forgetting this original problem, let's say we do our antiderivative with respect to x, and we get the x squared over 2 ln y. And when we do the antiderivative with respect to y, let's say we actually get x squared over 2 ln y plus y. This term, this plus y, is not going to appear in your first antiderivative because it only has a y in it. And so you would include that in your final answer. Let's just erase this and go back to this problem. We're going to do several more examples, so hopefully I can make this more clear as we just do more and more examples. But basically the idea is you gather all the terms that you've collected from your two antiderivatives. We only have one here. It's x squared over 2 ln y. And so that is my potential function. If you ever want to check your work, it's actually not too bad to check it. You can just find the gradient vector of this potential function. So you can take its derivative with respect to x, and then you can take its derivative with respect to y, and make sure you get what you started with. And so that's a great way of checking your work. Now, if we have a three-dimensional vector field, that vector field is going to be conservative if and only if derivative of the z component with respect to y equals derivative of the y component respect to z, and derivative of your z component with respect to x equals derivative of your x component with respect to z. There's a little bit of a pattern here. And this one is the same expression, same test we had for our two-dimensional vectors. Derivative of your y component with respect to x equals derivative of your x component with respect to y. So this is how we can test if a three-dimensional vector field is conservative. So is the following vector field conservative? If so, find its potential function. So the x component is this 2xy plus 2e to the x z. That's my x component. And so to help me with the test, I just went ahead and found its derivative with respect to y and z. So with respect to the other variables. So derivative with respect to y would just be 2x. Derivative with respect to z is 2e to the x. Okay, and then my y component, the n, is just x squared. So derivative with respect to x is 2x. Derivative with respect to z is 0. And then finally, the p is 2e to the x. Derivative with respect to x is 2e to the x. Derivative with respect to y is 0. And so then I just want to check, so x component with respect to y, does that derivative equal y component with respect to x? Yes, those are the same. And then x component with respect to z, does that equal z component with respect to x? Yep, those are the same. And then finally, y component with respect to z, z component with respect to y. Yep, those two are the same as well. So yes, this is a conservative field. So now if I'm going to find its potential function, because this is in 3 dimensions, I'm going to set up 3 integrals. I'm going to be integrating my m with respect to x, the n with respect to y, and the p with respect to z. Okay, so I have that written down on the screen now, what I tried to say. So I'm going to integrate this m with respect to x, and then the potential function could have other terms with y's and z's. And then I'm going to integrate the n with respect to y, but keeping in mind that my potential function might have other terms with x's and z's. And then finally, I'll integrate my p with respect to z. Again, keeping in mind that any terms with just x's and y's will not appear. All right, so we'll take this m, integrate with respect to x. I get x squared y plus 2 to e to the x z. And then this right here is just saying there could be other terms with y's and z's that didn't appear in this antiderivative. Then I'm going to take my n, integrate that with respect to y, and I get x squared y. And then this is saying there could be additional terms with x's and z's that didn't pop up in this antiderivative. And then the last one, I'll take the p, integrate that with respect to z, and there could be other terms. Finally, I'm going to compare everything I have on the screen, and let's just check. Okay, so we've got an x squared y, and then notice the x squared y term doesn't have any z's, so it didn't appear in the third antiderivative, and that's perfectly fine. That's what this kxy is saying. Anything with just x's and y's wouldn't pop up in that third antiderivative. So x squared y is part of my potential function. And then I've got this 2e to the xz. Oh, that only has x's and z's, so it didn't appear in the second antiderivative. Oh, but it did appear in the third. So that's part of it. And then it looks like that's it. There are no terms that have just y's and z's that appeared. Okay, so again, I have it highlighted now. Maybe this looks nicer. There's my x squared y. It appeared in first 2 integrals. It didn't appear in the third because it only has x's and y's. The 2e to the xz appeared in all of the integrals except the middle one because it only has x's and z's. And then there were no terms with just y's and z's. And so those 2 terms, the x squared y plus 2e to the xz, that is my potential function. And again, if you're not sure, the nice thing is you can always check by finding your gradient, by taking the derivative of your answer with respect to x, y, and z, and making sure you get what you started with. Okay, so back to integrals. Let's try to connect these ideas that we've talked about. Let's see if we can evaluate this integral. So we've got a line integral. We're integrating this vector field f over the path that's shown in the picture. Okay, so that's the problem we're going to do. We learned how to compute a line integral like this in the previous section. We learned that we can take f dot r prime and integrate that with respect to t. Okay, so we learned how to do this in the previous section, but what I want to do in this video is see if we can apply our fundamental theorem for line integrals. If I take the m and find its derivative with respect to y, I get 2y, and that is the same thing I get when I take the derivative of n with respect to x. So yes, this is a conservative vector field. Because this is a conservative vector field, then I can actually evaluate this integral by finding my potential function. So that's the next thing I'm going to do. So my potential function, I'm going to take the m, and I'm going to integrate that with respect to x. I get 1/3 x cubed plus xy squared, plus there could be extra terms with y's. Then I'm going to take the n and integrate that with respect to y. Let's see, I get xy squared, and there could be extra terms with x's. Comparing these results, I am going to have an xy squared term, and then the 1/3 x cubed term. So there's my potential function, 1/3 x cubed plus xy squared. Now what the fundamental theorem tells us is I can actually compute this line integral by plugging in my endpoints and subtracting them. I do want to make sure I pay attention to the orientation of the curve, so I'm going to plug in where the path ends first, so 0, 1, and then I'll subtract where the path starts, which is 1, 0. So I can find this integral by just plugging in the endpoints of the curve. So if I plug x equals 0, y equals 1 into my potential function, I get 0. And if I plug x equal 1, y equals 0 into my potential function, I get 1/3. So 0 minus 1/3 is negative 1/3. And that's my answer. That's the answer to this integral. So the kind of interesting thing about these conservative vector fields is your line integral only depends on the endpoints. Actually, doesn't matter what kind of path this makes, only depends on what the endpoints are. Now, we could have done this problem the old way. I have it written out on the screen. I just want to really quickly show you that we get the same answer if we did it using the method we learned in the previous section. So we could have said this path right here is x equal cosine t, y equals sine t, from 0 to pi over 2. So that's my path. And then I could have taken my vector field and written that in terms of t by plugging in cosine for x, sine for y, did some simplifying. And then I could take the dot product of f with r prime. This is what I got. And again, I'm doing this pretty quickly simply because it's not really the focus of this video. I really just want to hopefully get the same answer. So we can take f dot r prime, and then we can integrate that from 0 to pi over 2, and we will actually get the exact same answer. You have to do a u substitution, but it turns out you end up getting the exact same answer of negative 1/3. And so that's kind of nice to see that the long way gave us the same answer, but that fundamental theorem is definitely a shortcut. It's much faster to do the problem with that fundamental theorem. The point that I really want to stress, though, is that fundamental theorem for line integrals only works if you have a conservative vector field. If you do not have a conservative vector field, unfortunately, that theorem does not apply. All right, so this next screen just has a bunch of statements kind of summarizing some of the things that I've alluded to already. Okay, so this first sentence right here is basically repeating what I just said. This integral is independent of path. And so what I mean by that is, as long as we start and end at the same place, doesn't matter what the path is, if and only if our vector field is conservative. And that comes from the fact we can only use that fundamental theorem if we have a conservative vector field, and then it is independent of path. Okay, and so then I've got 3 sentences that are kind of repeating the same thing. And these sentences we could say are equivalent because they're giving us the same information. So the first sentence says, if f is conservative, then f equals the gradient of some potential function. Okay, so that's kind of our first fact, just to start with. Conservative vector fields equal the gradient of some potential function. If that happens, if we have a conservative vector field, then the integral f dot dr is independent of path. So number 2 is only true if number 1 is true. Number 1 is true if only number 2 is true. Okay, so these 3 things are either all true or all false. And then finally, if we have a closed curve, something that starts and ends at the same place, this integral is going to equal 0. Because when you apply that fundamental theorem to a closed curve, your starting and your ending point are the same. You subtract them, you get 0. So if you have a conservative vector field, your line integral over that vector field is independent of path, and that line integral will equal 0 for every closed curve in that region. All right. So let's do another example. Let's see how this works for something with 3 dimensions. Let's see if we can find the integral of f dot dr for the vector field sine of z, I, minus z sine of y, j, plus x cosine z plus cosine y, k. And they're telling us that our path, c, is any path that connects the points 1, 0, negative 1 to 0, negative 1, 1. Now, the fact that this problem is telling me not explicitly what the path is, the problem is only giving me the endpoints of the path. Hopefully, this is a conservative vector field, because if it isn't, they have not given me enough information to do the problem. So the first thing I'm going to do is check, is this a conservative vector field? So I went ahead, I found all the appropriate partial derivatives. So let's see, if m is sine of z, you take the derivative with respect to y, you get 0. That's the same thing as your derivative of n with respect to x. When you take the derivative of m with respect to z, you get cosine z. Well, that's the same thing I got when I took my derivative of p with respect to x. And then finally, derivative of n with respect to y, n with respect to z is negative sine y, and that is the derivative of p with respect to y. So this is a conservative vector field, and so my next step is to go through and find the potential function. Sometimes I kind of skip that step of checking to see if it's conservative, because really another way you can check is if you try to find the potential function and the antiderivatives you get don't match, that's another clue that it's not conservative. So you can kind of see if you have a conservative vector field when you're finding these antiderivatives. They won't match if it's not conservative. And I'll show you what I mean by that in my next example. Okay, so I'm going to start with the m, and I'm going to integrate that with respect to x. I get x sine z. We just integrated with respect to x, so there could be additional terms with y's and z's. Let's see, middle component, negative z sine y. I'm going to integrate that with respect to y, and I got z cosine y. We integrated with respect to y. There could be terms with x's and z's. And then finally, I take that last component. I'm integrating with respect to z. So I got x sine z plus z cosine y. And again, there could be terms with x's and y's. So then comparing all of this information, let's see, we have an x sine z that didn't appear in the second integral, but that's okay because it only has x's and z's. Okay, it did appear in the third, that's good. So my potential function has an x sine z in it. And then let's see, we've got this z cosine y. It didn't appear in the first integral because it just has y's and z's, but it did appear down here, that's good. And then there's no terms with just x's and y's. So just those two terms, x sine z, z cosine y, that is my potential function. Because this is a conservative vector field, I can then find the integral by just evaluating my potential function at those two endpoints. So I'm going to take my endpoint 0, negative 1, 1, 0, negative 1, 1, plug that into my potential function. I get cosine of negative 1. And then the starting point 1, 0, negative 1, I put that into my potential function. I get sine of negative 1 minus 1. So my integral is going to be cosine negative 1 minus sine of negative 1 minus minus 1, so plus 1. And there's my final answer there. Let's do one more. Let's see if we can find the integral of f dot dr. We're given this vector field, and we're told C is now a line segment that connects 0, 0, 2 to 2, 0, 2. So if this vector field is conservative, then we can just use our fundamental theorem. And so I want to try to explain what I was saying earlier. If you want to skip that check with the m's and the n's, sometimes what I do is I just start finding my antiderivatives and comparing them. So let's see, we could take the y squared, and if we integrate that with respect to x, I get xy squared, could be y's and z's. Then I do the x squared, I get x squared y, could be x's and z's. At this point right now, I can tell you this is not conservative. And the reason I know it's not conservative is these terms don't match. I got an xy squared in the first antiderivative, but an x squared y in the second one. And so because those terms don't match, that tells me this is not conservative. I'm not going to be able to come up with a potential function. And then for completeness, you could do the third one as well and get something different. It's, I guess this z here should have occurred in this first antiderivative because it has an x in it. So that's another problem as well. So this is not conservative. This function, unfortunately, is not conservative. We could have done the m's and the n's and the p's, and we could see that it's not conservative there as well, because the m sub y does not equal the n sub x. Okay, so what does that mean? If this is not conservative, unfortunately, that means we cannot use our fundamental theorem, and we have to do this problem the long way, the method we learned in the previous video. So I'm going to have to come up with parametric equations to describe my line segment. And so these are the parametric equations I came up with. I noticed here when I compare these 2 points, the y's are always 0. The z's are always 2, right? So y is 0 in both, z is 2 in both. The only thing that's changing is the x values. So I just let x equal t, and then if we say t goes from 0 to 2, that will take me from one point to the next. So there's my parametric equations. So I am going to say my r is t02, so my r prime would be 1, 0, 0. And then I'm going to rewrite my vector field in terms of t. So I'm going to replace the y with 0, the x with t, the z with 2, so I get 0 t squared minus t minus 2. And then I'll take f dot r prime. Oh, I get 0 plus 0 plus 0 plus 0. Well, that's kind of nice because I guess if I integrate 0, I'll get 0, and that's my final answer. So I wasn't able to use my fundamental theorem for line integrals, but fortunately the numbers weren't too ugly on this one, and I have a final answer of 0. All right, that was the last example. As always, let me know if you have any questions.